Okay, so what I wanted to mention or talk about today was something that's kind of known, I guess, but not very frequently discussed or mentioned. About in quantum mechanics, you have like the Schrodinger's cat and the uncertainty principle. You have the square box. Okay, and the idea is that inside the box there's an unknown. You have this thing that you hasn't been measured yet, hasn't been observed yet. And so a lot of times you'll hear a description of the cat is both alive and dead at the same time until you measure or observe it, and then that causes the wave function to collapse into one state or the other, alive or dead, etc., or for particles, whatever. That can be interpreted a couple of ways. One, that I think was more popular years ago, was that was just a limitation of the observation, that the cat had a deterministic specific state, or that particle did or whatever. You just didn't know what it was, and your method of trying to measure it would influence the result. And so if you try to detect the position of that feather by touching it, in the act of touching it, you're moving the feather. And as you get smaller and smaller and tinier, just bouncing light off of something will move it. You start getting tinier and tinier, electron size, smaller, etc. And so that's when they started to say these things where, like, if you're trying to detect one thing, the act of using this detection mechanism causes this other thing. And since you can't detect two things at the same time, say its position and its momentum, you're going to be measuring one or the other. That always leaves a certain amount of uncertainty in the thing you're not measuring. Okay, so that's the generalishness. But and sometimes in fiction and so forth, and in some basic descriptions of quantum computers, they'll talk about how the quantum computer's qubits are in those multiple positions at the same time, but they're all doing calculations simultaneously. And then at the end, when you measure it, the wave function collapses into the equation that you wanted on the outside. Okay, now those are some examples of descriptions that you will hear and that I've heard. What's missing that I wanted to at least mention here is that the concept of the unobserved state, the unmeasured state, is itself a piece of complete 100% fiction. It is not possible in the real world for any state, any particle, any wave, no matter how subatomic tiny you get, there's no point at which it's not interacting with other things, that it is not, being measured, being, observed. Unless somebody wants to invoke some kind of new humans or magic, and it's just that humans are observing it that matters. It's like, well, unless you're doing some pseudoscience, metaphysical gibberish like that, then there's no box that you can make that quantum tunneling can't get through. That they've even had papers out recently that they don't, that they've done math saying that they think you can quantum tunnel out of a black hole, from the inside of the event horizon through it. You can quantum tunnel. And they've talked about how quantum tunneling, you can, and they've done some experiments where it suggests it might even be able to skip a certain amount of distance and, get faster than the speed of light or whatever. And so to have a state where something is unmeasured and so forth, then because things do have quantum tunneling and they do have those effects, that would mean that you have a box that has a 100% certainty cannot be quantum tunneled through from the outside in or from the inside out ever. And they won't ever want to admit to such a thing there. And even if you could do that, even if you want to ignore quantum tunneling for a moment, there's all kinds of other forces which you can't isolate from. To create a box or area or region of space that has absolutely zero magnetic fields, no magnetic field can penetrate inside of this thing. that's difficult. You can say that you reduced it, that they're minimized, and things like that. But to say zero, yeah, or electric fields, or radiation, or neutrinos, things that are weakly interacting with matter at all, that somehow can't possibly even get inside this box. Or even gravity itself. Gravity, the mass of the thing inside the box is sending information outside the box and interacting with things outside the box. If I'm using gravity as a means of detection, where I have your box and I have equipment where I can, in theory, detect the mass of the thing in the box, then its mass, then that, whether that mass is, if some people call relativistic mass, of the energy content or rest mass, either way it doesn't matter. You have this gravitational effect, and it will propagate through that box. There's no material you can make it out of that will prevent that, as far as I'm aware of, that will prevent it from propagating out of. There's not in an emptiness vacuum of space. There's no material you can make it out of, and that even goes for black holes. The event horizon does not prevent gravity from propagating from inside the black hole through the event horizon to the outside. That's why you get pulled in, because you got this curvature, because gravity gets out. And gravity gets in. This black hole over here and this black hole over here, they will tug on each other. This one's sending, is going over and tugging on that one, and this one's tugging on that one, or they're curving in space and falling in. Whichever description you want to use, it doesn't matter, because fundamentally, the gravity, it's detecting that thing. And like I said, unless you want to invoke some kind of humans or magic, it's that we humans observed it. It's like, it doesn't matter. The measurement was made. Whether I made the measurement because I felt the touch and that electromagnetic signal went up to my brain, or the cat touched it, or the pendulum hit it, or whatever. Whatever the thing is, but it's interacting. And there's no way to create that box that gravity doesn't get out of, that quantum tunneling can't get out of, that there's no no electric field, no magnetic field, no neutrinos, no form of anything can possibly ever get through this box. And that is impossible. Therefore, the thing to keep in mind, whenever you hear people talk about whether it be quantum computers and they're these uncertain states, or the Schrodinger's cat and it's alive and dead at the same time, the thing to always keep in the back of your mind is that it is always perpetually, continuously being observed and measured all the time. The universe is always doing this to everything at any scale you want to do. They have not found any amount of mass, no matter how tiny, that gravity doesn't, pull on, that it doesn't distort space. There's no amount of, tininess that escapes that issue. Now they've shown this reacts very weak, this particle reacts weakly with this one and so forth. And you can say that you made a box that is unlikely to have some, but you're not really making zero. You're reducing how much of an influence you have. But when there are things like gravity, then that is always perpetually pulling on it. It's just like, imagine if I have a rope here and there's something pulling on the other end of it. I know roughly how hard it's pulling. I know the direction it's pulling. I have information about that thing, and gravity's doing that for any of those tiny little things. And they can say, well, you have an uncertainty of position. Like, it could be here or it could be there. And it's like, no, gravity's pulling me in a specific place. If it were here and here at the same time, then I'd have gravity pulling on it at both times. It's being observed. It's being measured. Whether I'm doing it, or the rock's doing it, or the moon's doing it, or that dust particle's doing it, doesn't matter. It's still being done anyway. There is no unobserved, unmeasured state. Now, we humans might be oblivious to it, but that doesn't get you out of that problem. So just keep that in the back of your mind, that no matter what, whenever you hear those things in those descriptions, is that all of those things, even at the tiniest, smallest scales of time, distance, particle, whatever you want to say, there is no unobserved state. There's no human observed it, but the fact that, the other, no, that's not real. Okay, that's my ramble.